All right, we're looking at indefinite integrals and the net change theorem. All right, so we have discussed fundamental theory of calculus part 1. We've looked at fundamental theory of calculus part 2. And now we want to reformulate fundamental theory of calculus part 2 in a way that, like you see, they mentioned there, in a way that makes it easier to apply to science and engineering. That's the whole idea about this whole indefinite integrals. Indefinite integrals, what are those? Now, for part 1, we saw that, let me just get my pencil again. For part 1, we saw that if a function f is continuous, then you can say the integral for some constant a to some variable x of f of t dt is an antiderivative of f, all right? And then for part 2, we saw something like this. The integral from a to b f of x dx is found by just looking for the antiderivative and evaluating that antiderivative at the upper limit minus the antiderivative evaluated at the lower limit. All right. Now, what does this whole thing mean? It basically means that the definite integral is a number. Very important. Definite integral is a number. What does that mean? It means that if I give you an integral which is bounded, when I use the word bounded, it means you have the lower limit being some number, the upper limit being some number, some constant value. The output is going to be a number. All right. Whereas an antiderivative is a function. Here we go. So antiderivative is always a function because it's that function such that if you differentiate it, then you're going to get your original function. So it is a function. All right. So what we mean by indefinite integral, if you look at this notation quickly, all right, there's nothing there along the bound. So this notation integral, I don't put anything along the bound. F of x dx, that is what we call indefinite integral. So the word indefinite integral simply means it's an integral that is not bounded. So there's nothing on the bound. So you don't have any upper limit or lower limit. And very important, the integral f of s dx, this is, remember, this is your antiderivative, all right? Please don't forget, whenever you integrate, you do an indefinite integral, just add plus c, right? Although here it didn't mention it, but there should be a plus c. What's the use of this plus c? We've seen that before. We add the constant of integration because the plus c doesn't actually change our result. Remember, if you look at this graph here, so this graph here on the right, the curve is exactly the same curve. The plus c simply shifts the curve going upward or downward, all right? It doesn't actually change the curve. That's why the antiderivative, once you find the antiderivative, always add plus c, all right, when you're doing indefinite integrals. For example, let's look at this. If you integrate x squared, you just get x cubed over 3. And you see, we add that our guy there called plus c, the constant of integration. Very important. Why? Because there's so many possibilities. If I say c is equal to 2, I differentiate that, I'll get x squared. If I say c is 10, I differentiate this whole thing, I'll still get x squared. Because of that, too much possibilities, we just say plus c. And this is just a demonstration. If you differentiate that, you get x squared. Now, this is something that you need to remember because some of you usually make this mistake. The definite integral, let's use it. The definite integral equals to a number. So if I ask you a question, the integral of 1, 2 of x squared, the fact that you have some lower limit, you have some upper limit, the output must be a number. If I ask you an indefinite integral, remember indefinite means it's not bounded, there's no bound, no upper and lower limit. You should get a function, right? A function. This is your antiderivative, and you just say proceed. All right. Let's look at another possibility. If you integrate sec squared, you ask yourself, what do I differentiate to get sec squared of the tan? All right. So the integral of sec squared is tan, you just add plus c. Why? Because if you differentiate tan x plus c, you get sec squared. In summary, this is a table you need to remember, right? If you don't look at this table, you will be surprised at what's going to happen to you on the day of the exam. Please make sure you know these table of indefinite integers. Very, very important, all right? The reason why I say it's important because if you see any of this, you're welcome to just state the result. You don't have to show me or derive where they're coming from, all right? Once you see that, you just write, for example, if it's the integral of 1 over square 1 minus s squared, just tell me sine inverse, all right? And so on. So please look at this table, very, very important. Let's look at this easy example. It asks you for the integral of 10x to the power 4 minus 2x squared x. Firstly, you can split the integral or you can just go ahead and integrate each of this. So 10x to the power 4 becomes 10x to the power 5 divided by 5 minus 2, obviously the integral of 6 squared just done, and you just say plus c. Done. Straightforward and easy. So this one should be easy. Let me see if I can show you what it looks like in the memo. All right, hopefully you guys can see the memo. You can see there you just have 10x to the power 5 over 5 minus 2 10x plus c. You can simplify your result because you know 10 divided by 5, which is 2. So 2x to the power 5 minus 2 10x. Now the next question, we had to integrate this. So the integral from 0 to 16 of absolute value. All right, it's a very important one which you have to know. All right, absolute value x minus 8. Once you see an absolute value function, if I ask you to integrate an absolute value function, remember in test 2, I asked you where is this absolute value function differentiable. Right now, it's actually the integral of the absolute value function, so you can already see how important it is. The first you need to do is to tell me that this absolute value x minus 8 is either positive, which is just x minus 8, that is if x minus 8 is greater than equal to 0, and it becomes negative, so minus into x minus 8, which just becomes 8 minus x, if x minus 8 is less than 0. So simplify this whole thing here. You get this absolute value to be x minus 8 if x is greater than or equal to 8, and is 8 minus x if x is less than 8. So the first thing you need to do whenever you're integrating an absolute value function is to give me that definition of the absolute value function. Definition of absolute value function. Because once you do this, it becomes clear on what you're going to do next. Now, how do I integrate? Notice it, there is a property we saw that if I'm integrating and I have adjacent bounds, all right, I can actually split my integral into 2. So I'll show you now. I'm moving from 0 to 16, so this integral is from 0 all the way to 16. If I look at this definition of that absolute value function, the focus is around 8, right? And you see on both functions, I have 8. So that adjacent bound they're talking about is actually 8, all right? You see that I can move from 0 all the way to 8. I say plus the integral from 8 to 16. Be careful, you have different functions here. From 0 to 8, remember, it means that x is typically less than or equal to 8 in this case. Therefore, you're dealing with this second function, all right? And from 8 to 16, you see that x in this case is greater than or equal to 8. Therefore, you're dealing with that first function. So you need to choose the correct function. And obviously, if you integrate that, it becomes straightforward. Easy, everyone can do that. You get your answer very easily. All right. So this is just where the work is. So the biggest challenge that you have is to set this up. And from there, it's just straightforward because you just substitute the bounds. Remember, this is fundamental 2 of calculus part 2. Once you see upper limit and lower limit, it means that you need to get some constant as your final answer. Right? Let's see what the next question is. All right, we've already done this example. Now let's move on. The access to evaluate cos x over sine squared, cos theta over sine squared theta, right? Sometimes it's important to just simplify the expression. Don't be quick to try and see what to do or try to use some funny methods of solving this, just simplify it. Yeah, if I split this sine squared into sine times sine, notice what happens. 1 over sine is cosec and cos over sine is cot. This is something that we know. The integral of cosec and cot is just negative cosec. All right. So you see, all I did was manipulate this whole expression to something that I know, and it becomes easy to integrate. All right. And this one you can go try. It's straightforward. This is a polynomial. So you just have, if you integrate, you have 8x to the power 4 over 4, 3x to the power 3 over 3, just a plus c. The second one is fundamental 2 of calculus part 2, meaning that if you have to integrate and then substitute upper bound minus lower bound. Straightforward and easy. Similar to this, so this is also fundamental 2 of calculus part 2. You can integrate this, and this is easy. Take note of this guy there. You check on the table, this is just tan, right? Tan inverse. If you integrate 3 over x squared plus 1, you just get 3 tan inverse of x. All right. So 1 over x squared plus 1, the integral of that is arctan, because the derivative of tan inverse is just 1 over 1 plus x squared. Now, if I give you something like this, the first thing is to try and split. Remember, this denominator here applies to everything there at the top, meaning that you can split it out. So you end up with 2t squared divided by t squared. You see, you have 2. T squared root t divided by t squared, you get root of t. And then minus 1 over t squared, which is just t to the power minus 2. And then integrate that, apply your fundamental 2 of calculus by 2, and then you're good to go. Straightforward and easy. Right, there you go, you have some result. And that is it for 5.4, what we call the indefinite integral. So we'll look at definite and indefinite integrals now. All right, so everyone should be comfortable. The question action the assignment, you should be able to do it now. All right, so let's move to U substitution. All right, now we're going to discuss the substitution rule. The question is, why do we need a substitution rule? You can see so far, when we get integrals like this, we don't really know what to do, right? Because this is not something you can directly integrate, right? So for such kind of integral, we don't know what to do. So we're going to try and do change of variables, all right? For example, we move from the variable x to a new variable called u. You see how it works? If I let u, for example, to be this term there under the root, notice it, the derivative of u, which is du, it gives me 2x and dx, all right? Which is fine, because yeah, if you check outside, I have 2x, I have dx, right? And this whole integral here becomes root of u du, and we can now integrate this using the power rule of integration, and we add our c. There we go, and then we simply change the variable u back to x. That is u substitution. So in general, this method always works when you get functions of this form, right? So you have your u will be some function g of x such that the derivative of u actually exists in the same integral. You can see the derivative of g of x exists in that same integral. So you have a function and the derivative of that function appear in the same integral, then you know it's u substitution, right? All right, this is the definition for the substitution rule. They say if u equals to g of x, it's a differentiable function. Why is it differentiable? It should be something you can actually differentiate, all right? Whose range is an interval I, and f is actually continuous on that interval I. Then we see the integral f, remember this is just some form of composition, f of g of x, all right, times g prime of x dx is just f of u du. Why is this the case? If you let u to be g of x, the derivative of that will be g prime dx, which we'll just call du. That's why you have integral f of u du. Now there's a lot of examples. We'll go through each of them. Then I want you guys to focus on that. I'm sure for those of you that looked at the assignment, you probably have seen something that looks like that. All right. Let's go to our memo once again. Okay, I'm just going to zoom out so that we can see what's happening. So for the first one, let u in this case to be x to the power 4 plus 2. Why? Because the derivative will end up with an x cube, which exists. You can see there's an x cube outside there. Right. So let u to be that function such that the derivative of u exists in the same integral. If I let u to be x to the power 4 plus 2, and I then shift that, you end up with 4x cubed. This x cubed times dx exists already in my integral. The 4 is just a constant, so it's fine. Right? We can factor it out. So you see, if you do that, then this whole integral simply becomes cos of u times 1/4 du. So where I see x cubed dx, which is this term there and this last term, I just put 1/4 du. That is how we got this term here. And then cos of x to the power 4 plus 2, just cos of u. Take out the constant and then integrate cos of u. You have sine of u over 4 plus c. Don't forget the last step is to replace the u back to x. All right. Because the integral that I ask you is in terms of x, your final answer needs to be in terms of x. So always check that you've changed the variable back. All right. And then for this one, once you see a root, your u, if it's just a root, then your u will be everything under the root. All right. Just let u to be 2x plus 1. If you differentiate, in this case, you get a constant. If you make dx the subject, you have half du. If you do your change of variables, it just becomes integral of u to the power half, and that's also straightforward and easy. Now let's see if it gets any harder. In this case, like I mentioned before, always focus on that function under the root. So your u is going to be 1 minus 4x squared in this case. Du is minus 8x dx. You can see that when I differentiate x squared, it gives me something times x, and there's an x there. The key is that there should be something that exists in that integral that can cancel out, all right? So if you let your u to be a function and after differentiating it doesn't cancel with anything, then your u is wrong. And once you make the wrong u substitution, your integral won't get any simpler. It will get worse, all right? Once you try to do u substitution, and you're not heading towards any answer in the nearest future, then you know that your substitution is wrong. Just go back and see if you can change your substitution, all right? Try different possibilities. So in this case, we're going to have minus 1 over 8 u to the power minus half. You apply the power rule of integration, and if you substitute back the value of x to yourself. For e to the power 5x, that's straightforward, obviously, because you just let u to be 5x, right? Derivative of that, derivative of 5x is 5. If you make dx the subject, you have 1 over 5 du. Put it back in the integral, and you end up with something like that, all right? Now, the interesting one is this number 5, all right? Let's go over it step by step. If you understand this, then you should be able to attempt the one that I gave in the assignment. So the first thing you notice here is, because I told you to always focus on the function under the root, if you let u to be 1 plus x squared, or you differentiate that, take note you have 2x dx, all right? But then, if you look outside, you have x to the power 5, actually. You see that the derivative of u doesn't entirely cancel out with what is left outside, all right? But then there's a little bit of a trick here. And what is the trick? The trick is you can write x to the power 5 as x to the power 4, which is just x squared or squared, times x. There we go. Carefully, you see now your derivative now appears. You have some extra values there, which is x to the power 4, or x squared or squared. What do you do with that? You go back to this u substitution. The trick is to go back to the u substitution, make x squared the subject. If you make x squared the subject, you have u minus 1. And let's see what it looks like. So root of 1 plus x squared is just u to the power half, all right? And then x squared or squared, remember this is now x squared. X squared is u minus 1 from that u substitution. So x squared or squared becomes u minus 1 or squared. And x dx, you can see I have it here. X dx is just half du. There we go. Take the constant in front, multiply out, apply the power rule of integration, change u back to x, and you're done. All right. So when you let u to be a function, you differentiate u. Even if it doesn't entirely cancel out with the other function, you need to do the math, all right? You need to try and see if I can factor out something how can I manipulate the other function so that it works out nicely. All right. Everyone is happy with that example. Then we're going to move to example 6. All right, example 6 is a tan. All right. How do we integrate the tan function? We start by changing it, writing tan in terms of sine and cos. So integral of tan is integral of sine over cos. Let u, now you need to be careful, guys. If you differentiate sine, you can get cos. All right, so I'll be tempted to say let u be sine. And now the cos is at the bottom, so you can cancel with your derivative of sine. All right, so you let u to be the bottom function because sine is at the top and it's going to cancel out with this derivative of u. All right, don't let u to be sine instead. If you let u to be sine, the derivative cos, because cos is at the bottom, that is not going to help you in any way. All right, and if you substitute, you have minus integral 1 over u du. One thing you must remember is whenever you differentiate, you integrate 1 over x or 1 over u, please make sure you include the absolute value sign. All right. For example, the integral of 1 over x is the absolute value. So this is ln absolute value of x. Very important. You must always put absolute value. All right. Why do we force absolute value? Because there's no ln of a negative number in the first place. So what happens if x is actually negative? If you don't put the absolute value, you're trying to say there's a ln of a negative number. The absolute value takes care of the fact that x itself can actually be negative. That's why in this case you also see the absolute value sign there, right? Because u can be negative. The last step obviously is to just change the variable from u back to x, right, using the substitution that you made. Right, let's go back to a slide and see what example we can look at. All right, so yeah, they're giving you some more interesting examples. Go try this on your own. They tell you exactly let u to be cos. All right, even without telling you, you should know already that in this case you can let u to be cos. Why? The derivative of cos is sine. You can see there's a sign there. It's going to cancel with that du. All right. In this case, you can let u to be because if you differentiate x, you have 2x. You see there's an x outside there that will cancel with your derivative. Similarly, here, if you let u to be 2x plus x squared, the derivative is 2 plus 2x. And if you factor out 2, you have 2 into 1 plus x, which matches this term out here. All right, so this one is also straightforward and easy. Let's look at definite integral. So all the examples we've seen before, they were indefinite because there were no bounds. You didn't have upper and lower limits. Now, when it comes to definite integrals and you try to do substitution rule, you must apply something called the change of variable or change of bounds. Very important. Remember, the substitution rule requires us to do change of variable. But when it's definite, there's an extra condition. You need to do the change of limits or the change of bounds. All right. And this is just what it means. So if g prime is continuous on this closed interval ab, and f is continuous on the range of u equals to g of x, so this definite integral now becomes integral f of u du, but take note, a becomes g of a and b becomes g of b. It means change the limits as well, all right? Because your initial limit was dependent on x. When you change to u, the bounds needs to be also in terms of u. If you just maintain your x bound, then you're going to have a problem, all right? Those are some examples there. Let's see the memo quickly for those. All right, I'm going to zoom out again. All right, so look at the first one is the integral from 0 to 4 x over square root 1 plus 2x. All right, you let u, as usual, to be that function under the root, so you have 1 plus 2x. Du is just 2x dx. Take note there's an x there at the top that is going nowhere, but we can take care of that x by going back to this substitution and making x the subject. All right. So if you have a variable that is not disappearing after making your U substitution, go back to that U substitution, right, to make X the subject. So write X in terms of U. And you see this step here, this is an important step that I want you guys to notice. All right, the change of bounds. When X is 0, you ask yourself, what is U? U is 1. When X is 4, remember we're substituting in this U sub that we make here. X is 4, you put 4 in here, you get 9. So my new, so from 0 to 4, you see now I have my integral from 1 to 9, all right? Because everything now is in terms of U in this new integral. And in the place of X, like I said, make X a subject from your U substitution, and simplify, split this denominator, apply power rule of integration, apply fundamental to calculus part 2, and there you go, you have an answer. Similarly, for this one, you let U to be 3 minus 5x, du is just a constant, which is super cool, and then again, do your change of limits, all right? Actually say when X is 1, what is U? When X is 2, what is U? Because we were integrating from 1 to 2, now you'll be tempted to integrate from minus 2 to minus 7. But if you remember well, there's something that I want you earlier. I said that you cannot integrate from a bigger bound to a smaller bound. That's why you see us adding a negative sign. And the negative sign times the negative sign, that is why it changes to positive. And I flip the bound. You must always integrate from a lower bound to a higher bound. Minus 7 is lower than minus 2. That's why we swap the bounds. And the rest is easy. All right, let's go back to our slide. Symmetry. Right? What is symmetry? If a function is even, remember even means f of minus x equals to f of x. Then you integrate it from minus a to a. You can write this as 2 times from 0 to a. However, if the function is odd, meaning that f of minus x equals to minus f of x, the integral from minus a to a of f of x is equals to 0. This is going to help us a lot, all right? I can give you a very complex integral, and once you see that the bounds look alike, so it's from minus a number to the same positive value of that number, then keep in mind I'm trying to test for symmetry, all right? Okay, look at here, for example, to find the area under this shape, you can find the area of this one piece, and then just multiply that result by 2. That's what we're trying to say here when it comes to symmetry. Is an integral from 0 to a, and then multiply that times 2. Now look at this second one when it's odd. When it's odd, your output is definitely 0. Why? Because this area at the top will be positive, the area at the bottom here will be negative, and exactly the same value. So this area minus this area will just give you 0. Since they're exactly the same, the one is positive, one is negative. You see that if you add them, you just get 0. All right. This is another demonstration. Integral from minus 2 to 2. You see, this is the trick. Look at the bounds. You can see there's some similarity there from minus 2 to 2. If I'm testing symmetry, again, you know that x squared, is an even function. Therefore, it becomes 2 times from 0 to 2 of x squared dx, and there you go. Look at this. It's from minus 1 to 1. But x is an odd function. Why? Because f of minus x equals to minus f of x. So this whole thing here will just give you 0. You don't even have to show me this whole what, you know it will equal to 0. As long as you can prove there's an odd function, then you know your output is 0. And then this another one, they give us integral from minus 2 to 2. You need to test this function. You can see that this function is even. Therefore, you have 2 times from 0 to 2. And if you simplify, you get something like this. All right. All right, still another symmetry equation. You see how complicated it can be? For something like this, what can you use? You can do U substitution, you can't do any of those, all right? So the catch here is that although it looks so complicated and you don't know what to do here, check the bounds quickly to see something for symmetry, all right? In that case, you can see the bounds gives you an idea that maybe this is symmetric. So I go ahead and I test f of minus x. In this case, I get minus f of x. It means that it's odd. The output will just be 0, all right? In most of the time, if I give you this complicated stuff, you will try to keep it to be odd. Because if it's even, it means that you actually need to integrate it, all right? Of which at this point in time, you can actually integrate this, all right? Based on what you've been taught so far. And these are just some examples for you to go practice on U sub. So there you have some indefinite integers. There you have some definite integers. Now you can see this last one again. Look at the bound. You can see I'm testing for symmetry there, all right? So go try this for yourself. The solution, the PDF is already available on Blackboard, so you can try them and then check your answers. So I hope now with this, you're ready. We've covered all the scope for what we're supposed to do for this course. So our next step will be the exam. So make sure you study. Send me an email if you have any query. If you want to consult, make use of the tutors in the WhatsApp group. Next week is going to be the block week. We usually have a 1 week, which is called study week or block week, where you can still consult with the tutors. So make use of the tutors in preparation for your exams.